So in the last lecture video, we started off with section or chapter 7, and we went over some basic concepts that are involved in chapter 7, and also the overarching picture of what chapter 7 is all about. Today we're going to, or in this lecture video, we're going to try to do some numerical examples along with making confidence intervals. There's one really important thing that we need to get into, and that's going to be our decision rule for our confidence interval formula. And keep in mind, if we go back to the last page of our lecture notes from the last video, we looked at these two formulas here for confidence intervals. And in both of these formulas, we always start off with x bar plus or minus z sub alpha divided by 2. But like I pointed out in the last lecture video, what changes between these two formulas, it's what's inside this parentheses, more specifically what's in the numerator inside both these parentheses. If we know sigma, we're going to use sigma up in the numerator. However, if we don't know sigma, we're going to use S, which is our sample standard deviation instead. So now the question just becomes is, when do we use which one of these two formulas? Well, like I also pointed out in the last lecture video, we're still dealing with large samples. So we can only use these formulas whenever our sample size is greater than or equal to 30. So therefore, that brings us to this decision rule. And in this decision rule, let's take a look at this decision rule first. First off, we have to decide whether or not we're going to be up here in this top half or if we're going to be down here in this bottom half. So the first question that we want to ask ourselves is whether or not n is greater than or equal to 30. So I'm going to write that down here as the first question that we're going to ask ourselves whenever we do our problems in chapter 7. Is n, our sample size, greater than or equal to 30? And that's a yes or no answer to that question. Either it is greater than or equal to 30 or it's not. And depending on how we answer that question, it's going to determine which box that we're in. If we're up here in the top half, if we answer yes, or if we're down here in the bottom half, or if we're going to answer no. Then if we follow it, let's just say that we are greater than or equal to 30. We're going to be up here in the top half. Our second question then is sigma known? Here, we would either answer yes to that question. So here is sigma known. If we answer yes to that question and say sigma is known, then we're going to follow it up here. And we're going to use z sub alpha divided by 2. However, if we say that n is greater than or equal to 30, but sigma is not known, so we answer yes to the first question, but no to the second question down here, then it's also telling us that we're going to use z sub alpha divided by 2. And what exactly I mean with using z sub alpha divided by 2 is this. Just like I just pointed out those equations on the previous page in our notes, I'll put them back up here. Both of these formulas have x bar plus or minus. I'm going to skip the z sub alpha divided by 2 here for a second. And then times our numerator. Here we're always going to have some standard deviation. I'll abbreviate that as STAND.DEV for some standard deviation. Either we're going to use sigma if we know the population standard deviation, or S if we know the sample standard deviation. And then down here we're always going to have the square root of n. Now the question is this. What goes right here? And what we've seen so far is if n is greater than or equal to 30, whether or not sigma is known or sigma is unknown, we're always going to use z sub alpha divided by 2 right here in this spot in this formula. As we'll see here in a minute, it's either on the next page or the page after that. So this is in section 7.1, this first half right here. Section 7.2 is right here, so I think we get into 7.2 on the next page of the notes. Here is, if n is less than 30, now we're going to answer no to this first question. And if sigma is known, so we answer yes to the second question, we're still going to use z sub alpha divided by 2 here in this spot in the formula. But what's really, really, really important here is this. If we answer no to the first question, so we're down here, and we answer no to the second question, is sigma known, now we're going to be down here. And if we answer no to both of those, we're going to start to use something called t. So in all of these cases right here, we're always going to have z sub alpha divided by 2 right here in this spot, except for the situation where we answer no to both of these questions. The only time that we can ever get down here to this box is if we answer no to both of these questions. Other than that, we would always use z sub alpha divided by 2 here in this box, right, which is just this spot in our formula. And up here, we would just adjust the symbol that we're going to use for the standard deviation, sigma if we know sigma, or s if we don't know sigma. So these two questions are really, 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 really important. That's how we're going to start off literally almost every single question that we do in Chapter 7. So let's go ahead and start doing some of these numerical examples. Which is on the next page of the notes. Alright, so here we have it. So it says confidence interval for the population mean examples. A sample of size 49 has a sample mean of 35 and a population standard deviation of 14. Constructed 95% confidence interval for the population mean and interpret your results. So first off is this. Just like I've been doing for every single chapter so far this semester, the question that I always get is, if I'm sitting down for a test and I read a problem, how do I know that I should be doing stuff that we learned in Chapter 7? How do I know it's a Chapter 7 question, not a Chapter 6 or a Chapter 8 question or whatever other chapter it is? A lot of times people have difficulty in narrowing down what to apply and when to apply it. Well, one really big giveaway that this is a Chapter 7 question is that it's asking you to do a confidence interval. So even if you go back and you study stuff from old exams or old common final exams, if you're trying to figure out what questions to look at to practice stuff from Chapter 7, you can go through them pretty quickly. If you see them talking about a confidence interval, it's a Chapter 7 question. There's one or two other concepts that we're also going to discuss in Chapter 7, but the bulk of the information in Chapter 7 comes down to this confidence interval concept. So if you read a question and it says confidence interval, that's your buzzword that is a Chapter 7 question. So let's do it. All right. We're dealing with a Chapter 7 question. The first step in every single Chapter 7 question that we're going to do is we're going to ask ourselves those two questions that we just had on the previous page. Is n greater than or equal to 30, and is sigma, which is our population standard deviation, is that known? So let's go through it. A sample of size 49 has a sample mean of 35 and a population standard deviation of 14. So in that, it tells us that our sample size is 49. Question is n, little n, our sample size greater than or equal to 30? So we can definitely answer that as yes, because n is equal to 49. Then for the second question, is sigma known? Well, sigma is our population standard deviation, and it tells us here that our population standard deviation is 14. So again, we're going to say yes, and sigma is equal to 14. So based off of this, again, on the previous page of the notes, we said that the only time we would ever get down here to use t in this box is if we answered no to both of the questions. If we answered yes to at least one of the questions, we're always going to use z sub alpha divided by 2, right? If we answer yes to the first question, we have to be up here, and up here, we're only using z's. If we answer no to the first one, but yes to the second, now we're going to be in this spot right here. But the only time that we can ever get down to this t is if we answer no for the first question and no for the second question. Then we're going to use t in that spot. Alright, so we know that we're going to use z. We're going to use x bar plus or minus z sub alpha divided by 2 times something divided by the square root of n. Now what comes up here? We're always going to put our standard deviation up here. Here we know our population standard deviation, so we're going to put sigma here in this spot. Alright, so this is the formula that we're going to use for this confidence interval. Let's try to plug some numbers in there. We already said that sigma was 14, and we already said that little n, our sample size, was 49. So I'm going to plug those in. Now we still need to know what x bar is. Well, x bar is our sample mean, and here it tells us that our sample mean is equal to 35. So the only thing that we still need to know then is z sub alpha divided by 2, but that's where we left off the last lecture video. So let's go ahead and do this one together to jog our memories about this. We're looking, since we're dealing with z, we know that we're going to have a bell-shaped and symmetric distribution, or more specifically, it's going to be our standard normal distribution. We're looking for a 95% confidence interval, so our confidence level is equal to 95%. So again, between these two cutoffs is where we're going to have 95% as our confidence level. We know that our confidence level is given to us by 1 minus alpha. So therefore, alpha is equal to 5%, which is equal to 0.05. Remember that alpha is whatever is left over from our confidence level to 100%. So here it's at our confidence level is at 95%. To get to 100% is 5%, so therefore alpha is going to be equal to 5%. But what we're going to have over here then is here we're going to have 2.5% in this tail, and here we're going to have 2.5% in this tail. In order to make it 2.5% plus 95% plus 2.5% is 100%. Well, again, like I kept saying last video, since this is 2.5%, but alpha is 5%, this is the same thing as alpha divided by 2. So both of these tails have alpha divided by 2 in it. So therefore, what we were doing in the last lecture video, towards the end of the last lecture video, is we said the z values that we're looking up right here for the cutoffs are going to be what we call z sub alpha divided by 2's. So just like we did in the last lecture video, if this tail now has 2.5% in it, and we're trying to figure out the z value that corresponds to that, we're going to go to the back side of our z table where we have the negative z values. And here in the body of our table are percentages. So therefore, right, it's the percentage of the graph that's here shaded to the left of our cutoff. That's why it's called the cumulative normal probability table. So here we're going to look for 2.5% or 0.025. And we did this one in the last lecture video. If we go here to negative 1.96, we see that right here we have 0.025 or 2.5%. So therefore, right here, this z value is going to be negative 1.96, and this z value is going to be positive 1.96. Now, what I said in the last lecture video is one of the things that I'm always going to stick to in my explanation of this is I'm always going to consider the z sub alpha divided by 2 to be the positive number. Keep in mind that this one is above the mean, so it's positive anyways, but technically speaking, that this one right here is below the mean, so this one's going to be a negative z value. But in my explanation, I'm always going to refer to them as being positive z values. And that's going to play more of an issue once we get into Chapter 8, the way that I explain stuff in Chapter 8. But I'm going to start to get you a little bit familiar now with me about how I go about these z sub alpha divided by 2's. And again, that's just unique to the way that I explain stuff. But you'll see why once we get to Chapter 8. Either way, we're going to put 1.96 right here because we just looked up the z sub alpha divided by 2. And it doesn't matter if you think about it as adding a positive number or subtracting a negative number. Either way, right here, or we could add a negative number or subtract a positive number. One way or the other, nothing's going to change about these symbols if we use positive 1.96 here or negative 1.96. That's why I'm saying it doesn't make a whole lot of difference in Chapter 7. It's going to play more of a role in Chapter 8. Either way, now we have our formula, right, with values in it for our confidence interval. So if you do this arithmetic and you take 14 divided by the square root of 49, and we're going to call this the principal square root, so it's going to be 14 divided by 7, or just 2, and then 2 times 1.96. If we take 35 minus that and 35 plus that, so here let me be specific about it. This is going to be 35, this is going to be 3.92. Right, if you do this arithmetic right here, it comes out to 3.92. So therefore, if you take 35 minus 3.92, comes out to 31.08. And if you take 35 plus 3.92, it comes out to 38.92. So therefore, here, this right here is our confidence interval. So a couple of things about this. First off, since this is an interval, this value right here, 31.08, should be smaller than this value right here, 38.91. Because whenever you write an interval of values, you always start off at the smallest and go up into the largest. Sometimes people write these backwards, and it's technically incorrect. So make sure that you have the smaller number right here and the larger number right here, because we're giving an interval of values. The second thing is this. Sometimes you'll see this as 31.08 to 38.92, but with the square brackets instead of the round brackets or the parentheses. Now, technically speaking, both of these are correct statements. Because keep in mind here that we're dealing with z values, and for z values, we're dealing with a continuous random variable for the standard normal distribution. And we're looking at having a probability of 95%. So by just leaving away 31.08 and just leaving away 38.92, technically speaking, we're only leaving away one individual value of a continuous random variable that has a probability of exactly equal to 0%. Remember, that's a concept that we went over in Chapter 6, and also in Chapter 5, whenever we had strict inequality versus less than or equal to or greater than or equal to. So technically speaking, both of these notations are correct. The notation on exams that you're going to see a lot, both on my exams and on the final exams, tend to have these round brackets or these parentheses. Your textbook uses a lot of the square brackets, but keep in mind that regardless of which format that you see this in, since we're dealing with a continuous random variable, they're both accurate. So here, I'm going to give you the answer as such. We're asked to create a confidence interval. This is the confidence interval. And now we want to give an interpretation of our results. And the interpretation of our results is worded very, very, very specifically. And what our interpretation is this. we are 95% confident that the true population mean mu is in the interval that we just calculated out, which is 31.08 to 38.92. Now, like I just got done saying, the interpretation, the wording of the interpretation is very, very, very specific. It says we are 95% confident that the true population mean mu is in the interval 31.08 to 38.92. Now, what I always recommend to my class is this. If you remember this sentence, the only thing that's ever going to change in this sentence is what I'm putting in a box. These three boxes are the only things that are going to change in the interpretation that we're ever going to give in this class. Right? If we start off with a different confidence level, right? Here we happen to use 95. If we used 80% or 23% or whatever percentage that we got, this could change. Here we're looking at the mean mu. Later on we're going to look at proportions, and the population proportion is given to us by P. But technically speaking, we could have any population parameter here that we wanted to. But again, the most commonly used one is the mean mu. But this could change and will change towards the end of chapter 7. And obviously, if we have different numbers, we're going to calculate out different intervals. So then the interval values that we give could change too. But one thing that is a very, very, very common mistake is that when people say this, they say something to the effect of, there is a 95% probability that the population mean mu is in some interval. Saying that there's a 95% probability that mu is in that interval is fundamentally incorrect. And here's why. Let's boil this down to a simple just number line. If you have some number line, say that we have a number line that goes from 2, 3, 4, and 5. So let's consider the number line starting at 2 and going to 5. If I asked you, is 3 in this interval from 2 to 5, either 3 is in the interval or 3 is not in the interval. There's no probability about the fact of whether or not 3 is in this interval. It either is 100% in it or is 100% not in it. Here, 3 just happens to be in the interval, so therefore, yes, it is in the interval. Whereas 6 is 100% not in the interval. It would be fundamentally incorrect to say is that 3, there's only a 95% probability that 3 is in the interval from 2 to 5. That just doesn't make any sense. Well, that's exactly what we're doing whenever we're creating our intervals. We're creating our intervals. Either mu is in the interval or mu is not in the interval. We don't know which one of these intervals that we have, right? Like last class I said, suppose I picked one of these dots at random and I made the interval, and I didn't tell you what dot I picked, but I made the interval in this exact same way. The only thing that you can say is that you're 95% confident that mu is in that interval. There's no probability of whether or not mu is in that interval or not. So therefore, if you ever have to provide an interpretation, if you mention the word probability in there at all, chances are you're going to get 0 credit for that interpretation. So that's why I, again, always recommend my students to remember this sentence, because the only things that you're ever going to change out are what's inside the box. All right, let's go on to number 2. Number 2 is really similar to number 1. So if you want to take a minute, pause the video, give this one a chance by yourself, now would be a good time to pause the video and then start it again and see if you got the answer correct. All right, so let's do it. In a study of amounts of time required for room service delivery at a newly opened Radisson hotel, 45 deliveries had a mean time of 24.2 minutes and a standard deviation of 8.7 minutes. What is the 90% confidence interval for the mean time of deliveries? And again, interpret your results. Alright, so first off is this. How do we know that this is a Chapter 7 question? The way that we know that this is a Chapter 7 question is that it asks us to create some kind of confidence interval. Knowing that it's asking us to create a confidence interval signifies to us that it could only be a Chapter 7 question. And the way that we always start Chapter 7 questions is what? How do we start every Chapter 7 question? The two questions. Is n greater than or equal to 30? And is sigma known? That's how we're going to start off these Chapter 7 questions. So let's do it. Is n greater than or equal to 30? Is our sample size greater than or equal to 30? The answer to that is yes. We're looking at 45 deliveries. We're looking at 45 deliveries, so therefore we're going to say yes to this one because little n is equal to 45, and 45 most certainly is greater than or equal to 30. The second question is sigma known? And the answer to that is no. Sigma is not known. Keep in mind that sigma refers to our population standard deviation. Our population standard deviation is sigma. Here it tells us that for these 45 deliveries, which we already agreed on was our sample size, so we're dealing with a sample. For the sample of 45 deliveries, it had a mean and a standard deviation. So therefore, the standard deviation applies to the sample. So S is equal to 8.7. A really important indicator that you're dealing with the population standard deviation is that it will literally say population standard deviation. Now, obviously, you can mess around with the wording a little bit, right? When it comes down to the English, you can switch stuff around. But a really, really, really good indication that you have the population standard deviation, it will literally say population standard deviation. Now, if it does not say population standard deviation, read the question really, really carefully. Is the standard deviation talking about the sample, or is the standard deviation talking about the population? So again, if it says population standard deviation, that's 100% that you know sigma. If it does not explicitly use the word population, like we have in this problem, that's when I recommend read over the question super carefully, because sometimes they'll be talking about the sample standard deviation, and sometimes they'll be talking about the population standard deviation. Here it's talking about the sample standard deviation. All right, so again, we answered yes to one question, no to the other question. The only time that we're ever going to use T is if we answer no to both questions. As long as we answer yes to at least one question, we're going to use z-values. So again, here, the bare bones of the formula that we can always immediately write down is this. That's our bare bones. If you start off with that, you're good to go. Now, up here in our numerator, we're always going to write down some standard deviation. If we know the population standard deviation, we're going to put it here. If we know the sample standard deviation, if we don't know the population standard deviation, we're definitely going to know the sample standard deviation. So here, like we have in this case, we're going to use S. They're never going to give you both standard deviations for the population and for the sample. And even if they did, as long as you know sigma, you're going to use sigma. If you don't know sigma, you're going to use S. So up here, we're going to use this. And like I said before, if we answer yes to at least one of those questions, we're going to use z sub alpha divided by 2. Alright, so here we have our bare bones formula. We filled in the things that will change. And now we can start plugging numbers into this. We already said that S was equal to 8.7 and that N is equal to 45. X bar is our sample mean. Our sample mean is 24.2. So now the only thing that we still need to know is what z sub alpha divided by 2 is. And that's why we practiced it a lot before we got to these types of problems. So let's do it. Since we're using z-values, we know that we can use our standard normal distribution. Here in the middle is where we're going to put our confidence level. And now our confidence level is 90%. Our confidence levels, what's the formula that goes along with a confidence level? The formula for a confidence level is 1 minus alpha. So therefore, here, if we have 90% right here, we're going to have 5% over here and 5% over here for a total of 100%. And since 1 minus alpha is equal to 90%, we've always said that alpha is whatever is left over between our confidence level and 100%. So therefore, alpha is equal to 10% or 0.1. So therefore, 5% is equal to alpha divided by 2. So we have alpha divided by 2 over here and alpha divided by 2 over there. We're trying to figure out what our z sub alpha divided by 2's are. So again, since here in this tail we have alpha divided by 2 and these right here are the cutoffs for our tails, that's where that alpha divided by 2 notation comes from. What we're going to try to do now is we're going to try to figure out the z value that goes along with this 5%. Just like we did before, if we go to our z table, in the body of our z table are percentages. We're going to go hunting for 5%. We already did this one last time, the last lecture video, and we saw that 5% or 0.05 is right in the middle between negative 1.64 and negative 1.65. So like I said in the last lecture video, we can use the z value of 1.645. Alright, so now we have the values filled in into our formula. Now we're just left with arithmetic. If you do the arithmetic, this comes out to 22.07 to 26.33. Again, make sure that you have the lower value here and the larger value here. And again, it does not matter whether or not you have the round brackets or the square brackets or the parentheses and the brackets. Alright. Last, we still need to interpret our results because we now have our confidence interval, right? This right here, this is an interval. That is our confidence interval. So we just need to provide an interpretation. And our interpretation is what? Again, we are 90% confident that the true population mean mu is in the interval, what we just calculated out, 22.07 to 26.33. And again, we have the exact same sentence. The only things that will ever potentially change in the sentence, at least in this class, are these three things that I just surrounded by those boxes. Here we have a 90% confidence level instead of a 95% confidence level like we did before. We're still looking at the mean, so this isn't going to change. The only thing that this is ever going to change to in this class is the proportion P. You're either only going to have the mean mu or proportion P in this second box. And then lastly, the last box is just going to be the interval that we calculate out. And obviously that's going to change with the numbers that we have. Alright. So, those were two examples for large sample estimation of the population mean. Now we're going to finish off section 7.1 and go into section 7.2 that deals with small sample estimation of the population mean. So what we're going to now do is, instead of using large sample estimation of the population mean, we're still going to estimate our population mean, but now we're going to be dealing with small samples. Alright, again, what does it mean for a sample to be small? Well, when we're looking at the means, we're saying that a sample is large whenever our sample size is greater than or equal to 30, right? When we're dealing with proportions, it's a little bit different, but when we're dealing with the mean, we need to have an n greater than or equal to 30. So therefore, we're going to look at small, so all that that's going to mean now is that n is going to be less than 30. Whenever n is less than 30, and we don't know a characteristic about our population, if we don't know sigma about our population, so if we have a small sample size, but we don't know sigma, right? If we answer no to both of these questions, now we can end up down here with t values. Now, keep in mind here is this, and this is just a technicality for right now. You don't really have to remember too much about this for right now. Once we come back and talk about this a little bit more later, we still want to make sure that our population is normally distributed. But let's just leave that as a side note for right now. And once it becomes important, I'll make sure that I mention this to you again. But right now we're going to be dealing with n that's less than 30. And when we deal with n that's less than 30, instead of using our normal distribution, we're going to use what's called the student's t distribution. So let's take a look at the student's t distribution. Here we have some student's t distribution. And as you can see, right, there's three of them right here. As you can see, they're all bell-shaped and symmetric. So they have that in common with the normal distribution, that they're bell-shaped and symmetric. But here's something that's really important. We have these things that are called degrees of freedom, right? Degrees of freedom, we're going to abbreviate that as DF. So DF stands for degrees of freedom. Now, the degrees of freedom that we're going to get, for right now, you can remember that these degrees of freedom, or DF, is equal to little n minus 1. That little n is still our sample size. So our degrees of freedom is just going to be 1 less than our sample size, or our sample size minus 1. So here, let's take a look at this. If degrees of freedom is equal to 5, how big is our sample size? Well, if degrees of freedom so far is little n minus 1, and I'm going to say more about that here in a minute, but if degrees of freedom is equal to little n minus 1, then here our sample size, in order to get 5 degrees of freedom, we have to have a sample size of 6. If we want to get 15 degrees of freedom, our sample size must be 16. And if we want to get 25 degrees of freedom, our sample size must be 26. Now, if we would just keep on going on forever and ever and ever, eventually we're going to get to something that has a large number of degrees of freedom. And if we get something that has a large number of degrees of freedom, right? If you look at all of this, the one that had the smallest degrees of freedom was this little one on the inside. As degrees of freedom went up, so did our distribution right here. And as the degrees of freedom went higher, all the way up to where we are now in the one that I drew in. And this one right here, all the way at the top, this is a normal distribution. So the student's t distribution, as our degrees of freedom get higher and higher and higher, converges to the normal distribution. So if we had, say, a sample size of 30, so our degrees of freedom would be equal to 29, we would get something that looks super darn close to our normal distribution. And then that's where we get this general rule from that we had when we were working with the central limit theorem before. That as our sample size gets to be 30 and greater, the distribution that we're looking at is super close to the normal distribution, so we can use the normal distribution as an approximation. So as we keep on going higher and higher and higher, obviously we can go above a sample size of 30, and all that we're doing is we're getting closer and closer and closer to the normal distribution. So let's talk about what these degrees of freedom are. These degrees of freedom they're a little bit technical. Technically speaking, the degrees of freedom is how many things do you have that can vary freely whenever you're calculating out an estimate or whenever you're calculating out a number. So here, the textbook definition, your textbook definition of what the degrees of freedom is, it says it's a number that specifies a particular t distribution and that is computed based off of the sample size. And that's true for what we're doing, but that's not a fantastic definition of what degrees of freedom are, but it's good enough for what we're doing here. Just keep in mind that if you go on, we're also going to revisit the degrees of freedom later on in a future chapter. And especially if you go on and you take higher level statistics classes, you're definitely going to come across a different definition of what a degrees of freedom are. So just keep in mind that this definition that your book provides you is really specific to what we're trying to accomplish here. Alright. If we go on and we look at this next definitions box, this next definitions box should be really, really familiar to you based off of the definitions box that we've seen earlier. This one right here when we were dealing with large sample confidence intervals. Here again, like we had before, we either can know sigma or not know sigma. Here again, we're either going to use sigma in our numerator if we know it. If we don't know it, we're going to use our sample standard deviation S instead. But now what's really important is this. If we have a small sample and we don't know sigma, we answered no to those two questions that we came up with. And therefore here, what I was describing as in that box, we're going to now use t instead. Other than that, the concepts that we have in here in this box still remain the same as in this box. We're still going to use our point estimate x bar. We're going to add a margin of error to it and subtract a margin of error from it in order to create a confidence interval. But now, the margin of error is what we have after this plus or minus symbol. So therefore, the way that we calculate out the margin of error is going to be a little bit different in certain cases whenever we have small sample sizes and we don't know sigma. Alright, but let's go on and do some examples in section 7.2. Alright, here it says, for number 1, a sample of size 15 is drawn from a normally distributed population and has a sample mean of 35 and a sample standard deviation of 14. Construct a 95% confidence interval for the population mean and interpret your results. We're going to go about these questions the exact same way that we went about the questions that we just got done doing that look similar to this. And that is this. How do we know that this is a Chapter 7 question? The way that we know that this is a Chapter 7 question is that it talks about a confidence interval. Whenever we see a question that says confidence interval in it, we know that it's a Chapter 7 question. Now that we know it's a Chapter 7 question, how do we start them off? With those two questions. Is n greater than or equal to 30? And is sigma known? So, is n greater than or equal to 30? No. It tells us that we have a sample size of 15. So, n is equal to 15. Do we know our population standard deviation sigma? No. It tells us that we have a sample standard deviation of 14. So therefore, S is equal to 14. And now, we're in that really super important spot where we answered no to both of those questions. So therefore, for the bare bones of our formula, we can still have x bar plus or minus something times something divided by the square root of n. We can still use this as our bare bones. In our numerator here, we're going to have some kind of standard deviation. So here we're going to use s. Since we don't know sigma, we're going to use s instead. But now right here, since we answered no to both of the questions, this is the only time that we would ever use t sub alpha divided by 2. T sub alpha divided by 2. Alright, so again, the only time that we're going to use t here is if we answer no to both these questions. That's why it's so important to start these problems off by answering those questions. Alright, x bar in this problem, our sample mean is equal to 35. I'm going to skip over t sub alpha divided by 2 here for a second because we already said that s is equal to 14 and n is equal to 15. Little n is equal to 15. Now we just need to figure out what is our t value. And for that we need to have a new table. And it's going to be this table right here. This is our table for the critical values of t. And I'm going to post this to Canvas. If you go to Files on the Canvas page for this class, I have posted this table on there for you. And just like the Z table, this table has two sides to it. Here, this is the front side. Here, this is the back side. Or what I'm going to call the front side and the back side. The front side is the side where if you look up here, it has that DF, which stands for degrees of freedom. And it starts off at 1 and keeps on going. And then the back side, you also have the DF for degrees of freedom, but there it starts off at 51. I'm going to call this the back side and this the front side. So let's take a look at this. We have right here the DF. The DF column is our degrees of freedom column. And again, remember that the degrees of freedom is equal to little n minus 1 so far in this section. Again, like I said, we're going to revisit that a little bit later. But for right now, you can remember that our degrees of freedom is equal to little n minus 1. Up here in the first row, we have t's with subscripts. You can imagine that these t subscripts are alpha divided by 2. Later on, once we get into chapter 8 and stuff, we're going to switch it up a little bit. But for right now, you can remember that those subscripts are the exact same thing as our alpha divided by 2. It's the same alpha divided by 2 that we got for whenever we were using z values before. So here, let's take a look at that. We're using alpha divided by 2. What we're going to do next is we're going to do two things. We're going to figure out what column we're going to be in based off of our alpha divided by 2. And then we're going to figure out what row we need to be in based off of our degrees of freedom. So let's do it. What we did before, we're going to do the exact same way. We're using t values, and like we saw before in the previous page of notes, t values still come from bell-shaped and symmetric distributions. They're now just a little bit slightly different than our normal distribution. They're flatter with wider tails, but here they're nevertheless bell-shaped and symmetric. Just like we did before, we want to have 95% in between these two cutoffs. And since that is still our confidence level, that is still given to us by the formula of 1 minus alpha. Alpha then is going to be whatever is left over to 100%. So that's 5%, since here we have 95%, or 0.05. Since we're going to put 2.5% in this tail and 2.5% in this tail, since it's symmetric, then we have 2.5% plus 95% plus 2.5% is 100%. So again, this tail is the same thing as alpha divided by 2, since alpha is 5% and this is 2.5%. So alpha divided by 2. So here's the really, really important thing. Alpha divided by 2 is what we're going to use here for our subscript. So therefore, alpha divided by 2 is the same thing as 0.025, right? 2.5% is the same thing as 0.025. So we're going to try to find the t for alpha divided by 2 that is the same thing as t of 0.025. Here I just swapped out alpha divided by 2 for 0.025. Like I said, when we were looking at the t table, we're going to use what alpha divided by 2 that we have in order to figure out what column we're going to be in. Well, since our alpha divided by 2 is 0.025, this column right here has t sub 0.025, so we're going to work in this column right here. The next thing that we need to know is what our degrees of freedom are in order to figure out what row we're going to be in. So let's figure out what our degrees of freedom are. Our degrees of freedom is equal to little n minus 1. What is little n in this problem? We already said it was equal to 15. So therefore we have 15 minus 1, which is just the same thing as 14. So we know that our subscript is going to be 0.025. And our degrees of freedom is little n minus 1, which comes out to 14. So therefore, if we go back to this table, we're going to use this column because it's 0.025, and we have 14 degrees of freedom, so we're going to be in this row. And where these two things meet up, we see the value of 2.145. 2.145, that is our t value. So, the body of this table now is no longer percentages. In the t table, the body of this table is now t values. That's a big difference between the t value, the t table here, and the z value that we were using before. The body of this table now has t values. But we just looked up that we're going to use 2.145, so therefore we can plug 2.145 in for t sub alpha divided by 2. Now, we're pretty much right back to where we were before. We're going to do this arithmetic. If you do this arithmetic, it comes out to 27.2 to 42.8. Again, do this over here, and then subtract it from 35 to get this, add it to 35 in order to get this, and now we have our confidence interval. Lastly, as always, we're going to provide an interpretation, and our interpretation is we are, we are 95% confident that the true population mean mu is in the interval 27.2 to 42.8. And there we have it. Alright, let's do one more problem then, and then we'll call it quits for this lecture video. Actually, you know what? What the heck? We'll pause this lecture video here. You can give this next problem a shot by yourself, and then we'll do this next problem together at the beginning of the next lecture video.